Today we are going to talk about the Ruby concurrent programming. So, yeah, so to make everybody know this topic a lot better, I will just go over what Ruby concurrent programming is. So basically, what is concurrent programming by definition? So concurrent programming is mean that several computations are executed during overlapping time periods instead of sequentially. So instead of running one thing at a time, concurrent means that you can run multiple things at a time. It doesn't necessarily need to be parallel, but this means that you can have like several things in your task list that you're running them one by one. Like you can jump around them. Does not get blocked by one because it's in sequential. That if one thing is running for a long time, then you just block. Rather than if it's concurrently, the CPU scheduler can schedule to jump to another thing, tell it to do another thing. So, however, why do we need the concurrent programming? There are two main reasons. One is the I/O bounds, which is like everyone knows that in the web application that we spend lots of time to reading things from database. So those database call will usually take a long time. So it's like concurrent programming is one way to avoid I/O block, which just means that when we're waiting for the database to respond, we can actually do the other things. Starting, we're waiting for response. And after the other thing is blocked, then we jump back to the original thing, and then we realize, oh, the database is okay. Then we continue the process. So this is one thing. It's not only database, but it's also the web connection, the disk read, those mechanic things will usually take a really long time. So another thing is the CPU bound. So right now it's like everybody know the CPU is like have multi-core. So one of the way to use the full power of CPU is to separate your tasks into a concurrent small job. You can run them in different CPU. So you can allocate the maximum amount of CPU power by running the things concurrently. So those are two main reasons. So let's talk about the thread. So basically we are always in a thread. So whenever you run the application, you're running your process. And that process will usually have at least one thread inside of it. So in the Ruby, you can basically call the Thread.current to get your current thread instance, which is a wrapped object of the native thread. So by definition, the thread is the smallest sequence of program instruction set. So basically means a series of instructions. And a thread will also have a wrap process. So you can, in Ruby, you can always call the process.pib to get your process PID. And in the Unix command line, you can also always type PS to get your process list. So here's some comparison between the process and thread. So process, by definition, is that when you fork, it's usually to create a new process. You're going to copy all the memory space. You're going to allocate a new memory space, that including all the previous process have. Which is like if you're running a Rails application, when you fork a process, basically you're going to copy all over the Rails framework that you load in memory, and assign it to another space that you just allocate for that process. Which means this process is really heavy and takes a lot of extra memory. Versus the thread is actually in the process. So basically you don't have to copy all the memory to a new location. Basically another thread can directly access this memory. So basically the thread is really lightweight. You can share the memory with other threads. And there are another things like when you fork the process, when the process dies, then the sub-process you fork might not know their parent process is dead. Because the communication between processes is really hard. So it's like you might generate some zombie process when you fork and just manage them well. Or maybe this master process die. Versus the thread, the thread basically is a part of the process. So when the parent process is dead, which is maybe the main thread is dead, then everything will get killed too. So you don't have anything called zombie thread because it's wrapping the process. So because of the memory that you fork and you copy, so when you are context switch, the CPU scheduler detect some process being blocked. And you try to switch from this process to another process. That process will cost a lot of memory because you're going to reload everything from one process to another process. So you basically, the context switching between processes is really heavy and slow. Versus that thread, you can basically share most of the memory. So the context switching between threads is really lightweight and fast.
What is an example of context switching in like real life?
So context switching is like this is not a thing we can control, which is by the CPU. When CPU schedule detect some process is blocked, and they will automatically run the context switch. For example, we have Unicorn server, right? Unicorn server we run like 32 workers. So when one worker got blocked, the CPU will actually try to switch to load another worker, then run that request inside the worker. So that's the context switch. So we'll talk about the threads. So this is how you fork process. So for example, if I have a send email job, then I want to send 100 emails. So I can directly call fork, or you can call process.fork. So with this call, you'll basically generate another process, have another PID, have another thread inside the process, and run the code inside that fork. And then basically you have no access to the things that inside that fork. You can't share memory between them. Because when you call the fork, you basically copy everything to another process. So it's really hard to return any results from that fork. But however, then afterward you can call the process that wait until all the process you generate finish. And you can continue that. So versus the thread. So to use a thread inside Ruby, basically Ruby have a really good thread class in the Ruby core, which you can call the Thread.new. You can wrap a block inside the do. But basically with this code you write send email logic inside the thread, inside new thread. So basically with this code you generate 100 threads that's running inside one process, running concurrently. So afterward, you need to call the threads that join, which is mean that tell the CPU to tell the main thread to wait until other threads be finished. Or if you don't call the thread that join, this thing will just go through, and then it's just not waiting for those threads. So if this is the only thing you're running your code, then the process might just close, and those threads will be killed too. So basically you have to tell the main thread to wait until other threads finish.
Do you only want to do that if you don't want to continue processing anything until all the stuff's done? If you don't care, and if it can be asynchronous, you just keep going.
You can just keep going. That's fun. So
you're saying that if this thread finishes its execution and exits, the rest of the thread will just like exit even though it hasn't finished doing its thing.
yeah. But in the application that we usually run the server, so you should keep running, so it isn't necessary to join. But it's like here, we just try to wait until every thread is sending their email and finish, and they will run. So there's the rest of the computation. Comparison is like the process requires inter-process communication to return the results, or just sending any state or message. And versus thread, because you're sharing the same memory space, you can communicate via the shared memory. Then process is really easy to debug because everything you have is a separate instance. But thread is really hard to debug because in thread you might introduce a lot of like memory race condition, because you are sharing one memory. So if one thread is changing something, another thread is at the same time want to access the same thing, you'll have a race condition. They'll introduce lots of weird bugs. This is why the concurrent programming is hard. So we'll talk about a little bit about concurrent and parallel. Because concurrent is, by definition, is not definitely equal to parallel. Basically, it's really hard for you to control what's going to be parallel, because the thing is basically managed by the CPU scheduler. So concurrence means like when you have for example, you have a pair that are working on a tracker stories. So you have like multiple stories. So when one story got blocked, you might just switch to another story, continue working on that story, and switch back when the story is unblocked. Versus like parallel is like you have two pairs. You have two pairs working on a tracker. Each of the pair, they'll pick up the multiple story, and when the story got blocked, they'll pick up another story. That's mean the parallel. So it's like you can make your program concurrently, but you can't make sure that the program will run parallel. So maybe the same pair would still keep picking that story. So this one concept.
So is by definition what you're saying is, let's say there's only one core, right? If there's only one core, then even though your program is concurrent, but it will never run parallel.
I mentioned this because
Unless it has hyper-threading maybe, or hyper-threading is
There's
virtual.
only one
yeah.
core, then there's only one.
so in Ruby, everybody have some of them might heard that there's a thing called global interpreter block. So basically this thing will ensure that only one thread can be run at a time on a Ruby process. So by definition, so this thing is implemented by METs. There's a way to protect the C-level memory race condition. So basically stop you to run things from parallel. That's all it means. So why do we need this thing? You know, it's like, so there are, basically Ruby team seeing this GIL, Ruby interpreter lock, as a feature, but not a bug. Basically they are not going to plan to change it in the near future. They're talking about to remove that in Ruby 3 to introduce a new model to manage the memory to avoid those things, but they're still in discussion. But what this thing do is it prevent any possibility to corrupt the data while the Ruby is running. It's the easiest way to implement. And it also protect lots of things, like because in Ruby you can have the C extension. So when you include some C extension, how can you make sure those C code is thread safe? So this GIL is being introduced. One of the reasons is to protect the safety of your Ruby core to be not polluted by those extensions. So this thing is not exist in JRuby and Rubiness, which is like another Ruby implementation. So JRuby basically, the way they solve this, they just drop all the support for C extension. They just tell you to write everything in Java. And the Rubiness, they have more fine-grained lock control. I heard they have like 30 locks. They control each small part. And for the C extension, they are asking people to write thread safe code. They're trying to actively help people to, if they say some main package that's around thread safety, they'll try to send message to those like computer to tell them how to improve their package to be thread safe.
So any shared scope variable you're running to, you've got to put a lock around it.
Yeah.
Yeah.
We're going to talk about thread safe. So this is a sendmail example. So basically, we have a send count here. So for each thread, we're +1 for this count. And in the end, we wait for all threads to be finished, and we print the send count. So this string will be printed correctly. I think it will print correctly in the MRI, but it will not print correctly if you use JRuby or Rubinix. The main reason why is this +1 count. So for example, if you have multi-threads running at the same time, right? But it's like first we know those +=1 will be interpreting to the C code actually. So the C code is running actually multiple lines. you run the +1, and you run the equal. So it's like, while it's running +1, the other thread is assigning the memory to the same location. And then the context switch. And then another process is assigning the things to the thread. So this thing can separate to read. So first you read the send count. You gather the send count and you +1 and you assign them back. So it's like 3 steps. While you're processing the first step, if you got context switch, everything will screw. Because the other thing will read the wrong number. And after they add it, you assign the wrong number back. Every time you run, you'll just got a different number because this is completely random.
So concrete example would be like, I'm thread executing this, I read off, okay, there's one email sent, I'm gonna write context switches to you, you read there's one email sent, you up the count to 2, write the 2, you process it, okay, there are 2 emails sent, up the count to 3, write 3, I come back in, okay, time to write that 2. And that's what happens, right?
Basically, yes. So this is really terrible. But running in the MRI is more safe. Because basically you make sure you only have one thread. And usually for those, so send count +1 is really fast task. So usually the CPU won't context switch between you running this 3 small command.
So that's what makes it even nastier, is you don't notice these things until you get under really heavy load where you get lots of it, and then
It's
that's when
possible.
it starts out.
But generally, the MRI is protect you from those small things if you run things in parallel. If you run things concurrent. So
If you wanted to have this behave correctly in JRuby or Rubinius, what would you have to do?
So basically, we'll introduce that there's a lock mechanism in the Ruby. So here's another example. So if you in MRI, you're doing the thing like this. So first you load the count, and +1 to the count, and you send the mail, and then you assign the count back. I should write it wrong. It should be the count equal to send count equal to count. But however, this action have much higher probability to have the wrong number. It's because when the mailer sends email, CPU might just context switch. So when you assign it back, because the other thing is reading the send number too, so you basically got the wrong number back. So even MR can save in this case. So there's another example. So this thing, so those race conditions happen in lots of places. For example, you have a numbers array. And you try to assign the number array 1,000 times in 100 thread. And then you print out the length of the number in the end. So basically, it's the same thing. If you run in the JRuby or RubyNext, you'll probably get the wrong number. So because those push to the array things might override each other. So you might miss some of the element while you run in the thread. So there's another classic case which is mean check and print, check and pop. Because for example, you have a queue that you basically have like 100,000 numbers, and you want to check if the queue is not empty, I just pop 1. So if you run the same thing, if you run this in the RubyNext or JRuby, you have higher chance to be broken. Because when you check on this line, that you might get the wrong, it's not empty. And what if you context switch in here? The other people pop the last element in this queue, and then you run it here. And you pop the queue without anything, so you throw exception.
It's not empty, I'll just get the spoon that's right here. Oh.
So it's like, so there's Marshall and I used to work on one thing, there's RSPO in our code base that has had the similar bug. So we spend a lot of time to debug why this thing doesn't work. So basically the concept is every concurrent access to shared memory is not thread safe. So every time you want to access any shared memory in the thread, you have the possibility to pollute the data. So to avoid this, Ruby have things called mutex, mutual exclusion. So basically this thing is a lock. So when you wrap any code inside the mutex is synchronized, this means that before you run this block, the program will check this mutex is free. So if it is free, you'll try to obtain it, lock it, and run the code. So if it's not free, you'll just wait until you finish. So this is the simplest way to keep. So basically, for every time you access any shared data in your thread, basically you want to wrap it in the mutex, because then you make sure that only one thread can run in all time. So you can define the multiple thread for multiple memory access too.
So you just do this when you're writing to it, or also when you're reading to it?
Better to do that when you're reading, unless you're reading immutable things. If you're reading immutable things, there's not necessary to lock it. But if this thing will be multiplied by the other thread, you want to make sure that you're reading the right value, so you want to put a lock.
So you should try to keep whatever you're doing that usually should scope variable to the smallest amount of time because you're blocking other stuff.
Yeah.
Should you also have it when you're writing? Should you also have it for?
Yeah, you definitely need that when you're writing, because you don't want other people to override the thing you're writing.
Because you wouldn't need to, for immutable functions, you can't write.
So yeah, this is like a lock concept that whenever you run this code, you're going to get asked for this lock to be. If this lock is free, then you can do that also you have to. So here's some this thing is a thing called blocking queue, which is a thread safe data structure. Which means that when you push the things that you try to synchronize on the lock, try to make sure that only one thread can push to this data structure at the same time. But when we pop, you do the same thing. You try to synchronize and make sure only one thing can be popped. So in the Ruby, there's only one thread-safe data structure, which is just queue. So if in your Ruby application, you can use queue, which basically the implementation is just like this. So you can use the queue in Ruby to communicate between the threads. So another problem is deadlock. So deadlock basically means you have multiple mutual exclusion lock. They lock each other, or one does not release the lock. So for example, you have two lock. That one is mutex A, one is mutex B, and you have two threads running. And one thread is locked on A and try to ask for B. Another lock B and try to access A. And then if they're not lucky, then running on multiple, or they got context switch in between them, they will be locked. Because they won't release the lock until it's finished, and they'll just occupy and waiting forever. So this thing always happen in our application, right? So, and sometimes also happen on database, those deadlock situation. So there's a thing called condition variable that in Ruby 2. Basically, it's an API to signal thread to wait and resume. So for example, you have a mutex. In this case, that we have two threads. This I do it wrong, but the concept is you have two threads. One is generating the number, and one is reading the number. So when you are running a loop here, you can call it to wait for this mutex. So basically, when you call wait, you basically release the lock and tell the CPU to schedule another process to replace another thread to replace it until somebody signaled it. Then you'll say, okay, somebody wake me up. You'll try to go back and continue the process. So the conditional variable is a way to signal different process and release lock to wait things. So conclusion. So Abraham Lincoln used to say, as soon as you introduce a Thread concept, you are probably just introduced 5 new bugs to it. So another
Which are flaky bugs too, yeah, so they're not, yeah.
So another person used to say, if you see Thread constant in your code, you must be doing something wrong. So the conclusion is, the safest path to concurrency is, first, don't do it. Second, if you must do it, don't share data across thread. If you must share data across thread, don't share multiple data using mutable data. And if you really must share multiple data threads, synchronize access to that data. So it's like you need to lock data in one thread first.
But doesn't Puma, for example, I think run multiple threads, I think, like, so it's, you have to be thread safe if you're on Puma, I think. So
I think so. I
You
never
have
used
both
it,
modes.
but I think we might have some not safe code. For example, we have the application model of that current user. So if we are running Puma, this thing will be shared between multiple requests, I think.
Yeah.
So it's probably not safe.
Also,
Puma
how do
has
you-
both modes. You can run either this process or like threads. Threads is of course faster, but Sidekick is thread based, so for Sidekick,
So if you're, because we're running Unicorn, we can safely use that application model of that current user, because process is a independent memory space. But if we run a multiple thread, we might have one request from a user, which got load another user. We have so that model is not usable if we were
So
trying
one
to
of
use
the
it.
difficult things is even if you go through your application and you're really careful with all your shared scope variables, which your reason is, you still have all the little gems, you know? So how do you know your gems are gonna be thread safe?
Another thing is that if you're trying to load some code dynamically inside your another thread, it's not safe. We try to change the AST tree, you know, and try to change the Ruby class structure, then you will not be safe. But you can make sure that it's being loaded before the other thing is running. So basically, any modification to the shared memory will be dangerous in thread.
So what's the protection that MRI is providing with
They have
JRuby?
things called GIL, the Global Integrated Lock.
Right.
This is to make sure only one thread can be run at a time. But you still can't avoid the possibility to be context switch between the loading. So you might load dynamic generate one method in the middle, then you context switch. Another thing, try to call it. Maybe you call it and realize the method does not exist. Try to dynamic create it again.
All right, so
Cover that up.
that's,
Lots of possibility to pollute the data.
because of the possibility of context switches, it's not really protecting you against.
To
the
protect the button C code, that the Ruby won't crash just because you run something.
Right, right.
But in your code, you might still introduce more of those like risk condition if you're not writing code carefully.
So for the GIL, you mentioned that there's only one thread running at a time, right? But isn't that given though? Like in one process, you only have like one thread running at any given time, or are you saying that?
In one Ruby process, only one thread.
But isn't that like the norm though? I'm like they'll say one
It's
is
like
running.
you can have multiple threads, but
Right.
only CPU only schedule
Right.
one thread to run at a time. You can have multiple threads waiting in line, but they won't run parallel.
Right.
Only one CPU, one core
Right.
can run the process.
So that's how it works, I guess. And like what I'm asking is that's how it works in general. How is GIL in the GIL slide? You said that it makes sure that only one thread runs at any time. But if it's only running only one thread at any time, what is it giving?
What do you mean? So
Like
how
if you
the
go to-
GIL implement that?
If you go to the GIL slide,
I think so you never get them operating in parallel, so they never touch each other's memory.
but it never runs in parallel because in one, unlike the CPU never runs two things for a particular thread.
If you have multiple cores.
But this is for one thread, right? We're not talking about multiple cores.
No, even if you have multiple core, that only one core will run the one thread in Ruby process at the same time. So we have 2 threads in one process. The CPU will never pick up those together.
Alright.
So global interpretation logic is prevent in one Ruby process you have 2 threads. Then those 2 threads will never be run together.
So this is the reverse one, like in one thread, if there's only one process,
Yeah.
then to only, or actually the core is the main thing here. Alright.
So it's like you can run everything concurrently, but they will not be parallel because the things constraint.
But I still like the question that you were asking earlier about, like, we know Unicorn, basically there's a single process and the app code is you know, there's no memory sharing because there's one thread running in one process. And you get parallelism by having multiple unicorns. With Puma, because you have the potential for multiple threads, is there the GIO is still going to prevent multiple threads from running,
Yeah, you will still prevent mobile thread running.
but it doesn't prevent the context switching possibility. So if there's shared data,
So basically, it works as unicorn. The benefit is just take much less in memory. Because each process will have to copy all the rails and all the codes you have loaded to another worker.
Oh, so even Puma is thread safe because of the GIL thing. Is that what it is, or mostly thread safe?
It's not thread safe. So it's a tricky thing. The GIO give you some level of protection, but it doesn't give you 100% protection. So, however, there are lots of concurrent framework that basically the suggestion is that if you try to use those threads, you are trying to process something concurrently. Basically, you try to use those framework because those framework provides a much better protection or programming model to handle those things wisely. So basically, just don't implement those threads unless you know what you're doing. It's like there's an event machine which is running event loop. There's the thing service running event machine, and the actual cable I think is using the event machine. Another thing called an IO, is the new IO, the non-block IO, is also running event base. And the Sidekick, which is using the concurrent Ruby chain. But basically, Sidekick is implementing the thread by itself, but however, it's running some data structure on the concurrent Ruby package. There's another thing called celluloid, and then we can pronounce that. But celluloid basically is running an actor model. The Puma is running thread pool, and there's a package called Ruby Concurrent, which is right now the main package if you want to use the concurrent programming. So we'll just go over. Puma is a rack server that running threads and implement the thread pool with the mutex lock. And the Sidekick is a thread-based background processor. They use the concurrent Ruby with the map and atomic fixed data structure to implement the thread safety. And they have a processor run independent thread. And what processor do is to try to load things from the Redis. So they use Redis as a shared memory. So in that case, they won't have any risk condition. So this is the basic Sidekick structure. So basically, every processor is in their own thread, but they are getting the things from the fetcher, which is getting things from Ruby, from the Redis, and there's a manager in charge of passing this job into the processor. The celluloid is a little bit more tricky thing, using the things called actor model. So actor is the things that can receive and respond message. So for actor, you shouldn't modify the global variable. You should only communicate with the message. So this is an example of a counter celluloid. So this is an object-based counter. So when you include the celluloid, I believe, and then they will automatically implement a sync method on all method. So when you call async, that you actually trigger an actor. So this thing will not block. So it will not return the value instantly to you. So unless you call the value again, you'll try to wait until all the async job based on that object will finish. So you'll be like, if you call the actor async increment 41, and you call the actor count, you'll try to wait until that async job finishes. So if you don't access that, then your application will run really fast because that async call will run in different thread. So this is the active method. So then machine event loop, which I didn't read that code well. So basically it's using a reactor pattern, which is like you have a while loop that's running to listen to the idle. So if something that get passed in, they run the things. So in case that nothing is being blocked, everything is an event. So the concurrent Ruby is another modern comparison tools. They have lots of tools. They have like agents, future, promise, thread pool, supervisor, and more. They are all different concepts of concurrent programming that you can use. And it also provides you the thread state data structure like map, queue, or like even the integer, have thread state integer, you can call it incrementally. And it's inspired by lots of different languages, which they include lots of models. One of the models I really like is the Go, which they have things called Go channel. So basically, the Go channel concept is that everything is in the thread should be connected through the channel. So you can listen and assign things to that channel. So this is a simple application that you have a method for sum. That you have an array, you have 6 numbers. So you create a channel and run the Go routines, which is like press the first half of the array with the channel, press the second half of the array through the channel, and run the sum. After you add everything together, you'll try to put the sum back to the channel. So in here, that way you can try to get this XY back, we're calling the channel take. The channel this thing will block until the channel got new thing come in. So basically this channel take will basically just wait until the channel got new thing in.
Right.
So make sure that this part of the code will wait until those 2 jobs got finished, and then you continue run. Because using the channel to wait and pass through things is the Go practice. The thing is a really cool thing. And that's it.
Cool. Thank you.
Just remember the crucial advice, Max is not the threading guy, and so we are not the threading guy.
Well, it's the fundamental Ruby thing, what waste processor cycles rather than make programming harder, yeah.
You remember what Lincoln said?
Dying words.
Didn't know he
I
was
knew
a
this
word.
theater wasn't thread safe.
I think it's still good to know those button concepts. So
Right.
in the future, when you try to use something like Puma, or you try to use some more thread-friendly things, that you will think about possibility to be broken. Then it will also easier for you to fix those.
Yeah, I mean, the specific things that we said we're using in the accelerator are Sidekick and Puma, and I'm just, again, trying to understand what is there defensive coding that we need to do to use them effectively. It sounds like Sidekick introduces some thread safety mechanisms in Sidekick.
Yeah.
So-
Sidekick might be more easier than Puma. I mean, Puma probably we need to rewrite lots of things in this.
But if it's a greenfield application, like how do you take advantage? Let's say you want to take advantage of the potential for parallelism, because as you say, concurrency and parallelism are not the same thing. But let's say you want to take advantage of it, then some of the concerns you have, Puma's not solving that problem for you. You have to be aware of it when you write the code.
So basically, it's what Marshall do. Basically, freeze everything if you are doing the constant. So for those class shared things, you must freeze. And make sure nothing got modified.
If you're using thread, then you are sharing data, and if you are sharing data, you just slide. If you are actually using shared data, then the best thing that you can do is make it immutable, so that other threads won't override it.
We don't freeze our classes though.
Yeah. Well, basically for those servers, they'll try to eager load. Basically, they'll try to load when you fire the process, so that in case to prevent the further reading of those.
And if the server is spawning new threads to handle different requests, usually it's the session scope or global scope stuff. Like if you have local scope things inside of a function or an instance, the instance shouldn't be shared usually unless it's in a session scope or something.
Yeah. So it's like, but if you have something that dynamically loading code, dynamically generate code, this thing might be a problem. But so it's like if you have multiple thread, that all the codes will be loaded, even with before the thread is going to be fired, to make sure they can run on the same code base.
So if we have code that like dynamic rebuilds methods and stuff on something,
Dynamic load something,
yeah.
maybe call something that you manually call define method, some class, those things are not safe.
Right.
So I have to go see for dot score dot n